Thanks, man. Hey. Hi, everyone. Thanks for coming out. It's good to see people I know, people I don't know. Gather here on a very important day in American history when Nintendo announced that they're going to be releasing a 3DS XL bundle of Animal Crossing. I haven't everybody's seen that. It's literally the most exciting thing that's happened all day. To me, I'm not even lying. And it's built, and it comes with Animal Crossing on a 4 gig SD card, so that way it's always in your 3DS, which is my dream come true. But anyway, now we're talking about much older Nintendo stuff today. The title here is the 6502 and U. So there is an and U portion of this presentation where we have some hands-on. So if you have a laptop, either Windows or Mac, we'll be looking at some software together if you'd like later. If not, you could just follow along here. So the 6502, we're going to talk about that in a moment, but if you looked over the description, you know that it's a microprocessor that's responsible for a lot of classic computers and video game consoles. And I have a kind of strange relationship with it, and it's been one that's lasted for some time. And it started with a project I have called No Carrier, and I didn't know how to represent this, so I just took a screenshot of my website. And No Carrier is a project that's been going on for a long time and started performing in 2006. When I say performing, I mean that I use Nintendos, which have the 6502 microprocessor inside them, and I use them to VJ. So if you've ever seen anybody VJ, it's like it's projecting video on a projector or another surface, a wall, another surface during musical performances. And for about 6 years or so, I've been using Nintendos and video mixer to do live performance. And take a look. Right now, this looks the same as actually my website. And you can see here that I've released some software down here for the NES that we'll get into. But before I start releasing software, I do live performances here. This is one from Tokyo earlier this year, or last year, 2012. And you can see here, this is just audio coming through, kind of. There's performers down here, and behind a performer on stage, there are projections. And I used usually 3 Nintendos with a video mixer to project real-time video art there behind. And it changes, gets more complex over time, hopefully. And this is all done on a Nintendo, a couple of Nintendos. And yeah, this is the type of thing that really got me interested in learning the 6502 and learning how to program it, is because I wanted to do stuff like this. And besides that, I also do things like Vegavox. And Vegavox was done in 2007. This got a lot of publicity for Alex Maurer, a really talented chip musician. So he makes music on Nintendos. And in 2007, we released the first NES music album on a cartridge, and we've made subsequent follow-up ones. If you follow the LA Game Space, which is a new space that's starting out in LA later this year, we reissued some of these. They've been out of print for a long time. I think there's like 50 or 100 of some of these made. So I do use Nintendos in performance, but also write software that runs on cartridges that people can purchase or give away. And all the software that you see here is actually free and open source. And we'll be looking at that in a little bit. So again, No Carrier was kind of my entryway into the 6502 and learning to program for the Nintendo, Atari 2600, Commodore 64, and some other machines we'll talk about. Playpower was my other involvement with 6502. And this looks like a computer keyboard down here, but this is actually a really low-cost video game console that exists in India, many other countries. Comes with a mouse, and usually comes with a mouse, light gun, 2 controllers. They look like PlayStation controllers, as you can see, and this cartridge, which is which plugs in here. And for all intents and purposes, this is a modified 6502, basically a Nintendo in better packaging. And I worked with them for a number of years to develop educational games, develop educational games to distribute, rather, in countries around the world. This is a game that we developed that helps teach methods of preventing the spread of malaria. So we're trying to create games working with people in countries for release in those countries that would be culturally appropriate and educational. So we'll talk more about that later. But if you have followed this project before and haven't heard much from it, we will be releasing all the games that we did shortly, as well as a published paper coming out talking about the experiences that we have. We're working with designers and developers around the world, as well as traveling to different countries to do workshops and kind of get people involved at the volunteer level. So again, those are my big things I do with 6502. But to actually kind of take it back a step and really focus on the tech side of things, because the tech talk, I'm going to get started back in 1975, and that's when this chip came out. This is the 6502. And a lot of these dates, I got from Wikipedia because, believe it or not, I don't remember all this stuff. And they mostly refer to the US releases of many of the consoles and computers that I'm going to be talking about, the NTSC or American versions of these. So there some of the data that you'll see here that I'm going to talk about today varies from country to country. And yeah, so anyway, 1975, the 6502 came out. And it was MOS technology, and it was an 8-bit microprocessor. And some of the computers, again, that it was used in were the Apple IIe, the BBC Micro, the Atari 2600, the 800XL, Commodore 64, the Nintendo Entertainment System, and more. So there's a number of different, not only computers, but video game consoles that this microprocessor was used in. It was cheap, but it was fully featured. And I can't remember if I have this in my notes or not, which I can't figure out how to display on the screen anyway. But at the time, it was $25 in 1975 for one of these chips. So there's leading competitors like the 6800, the Motorola, was about $175. So when we say cheap, we're talking about, a lot cheaper for people that are just getting interested in developing, their own micro. And some technical background, and we'll see some of this in the code that we looked at. It has an 8-bit processor, and you hear that term thrown around a lot when we're talking about vintage or retro gaming. But it had a 16-bit address bus, which means, again, the width of the address bus has to do with how much memory that it can access. We think in terms of megahertz. We talk about computers now in terms of gigs. Back then, it was like 1 to 2 megahertz clock speed. So very, very slow. And again, the Nintendo clocked in somewhere around 1.7, I think. Okay, Andrew's shaking his head. That's good. So 1.79 even. I don't know if that's more accurate. But so yeah, crawling compared to today. And I've done workshops and artist talks so far and talked about Nintendos. We say that definitely, no matter what phone you have, even if you complain about your old phone, it's still much faster than this is ever going to be. And it has 8-bit accumulator register, which was represented as A. We'll see that in the code. 2 8-bit index registers, X and Y, and a 16-bit program counter. So these registers are memory locations where data can be stored, but they're only 8 bits, right? So that means that the maximum number that a lot of these can hold is 256, or 255, because we usually start counting from 0. So the amount of data and precision and that can be held and used in these older machines isn't anywhere near what we have today. But one of the interesting things, if you've ever played these video games or used these computers, you'll know that people did pretty amazing things with them. And therein lies, I think, a lot of the interest for people still today in older microprocessor technology. Like, why would you care about something this old from 1975? Didn't really, flourish until the 80s, and there's so much more you can do. But it's really interesting to see what you have to work with and what you can do with it. And there were 56 opcodes here. And this might not be something, even if you're programmer now, that you've ever come into know, this term opcode. Obviously it stands for operational code, and this is part of assembly language programming. And assembly language, you may have heard of it before, it's a very low-level programming language. When we say low-level versus high-level, of course we mean if we're talking about a low-level programming language, it is less abstract, and meaning that you're closer to the zeros and ones, where higher-level programming languages like JavaScript or Ruby or something like that, are more abstract, more like English. So I always have to go slow when I explain that because it's confusing, that things are more abstract or higher level. But when we say abstract, we're talking about that you can look at it and it looks like English. And when you look at assembly language programming, it just looks like numbers or closer to it. And again, opcodes are prevalent in assembly language programming. Again, there are 56 total for the 6502. So if you're interested in programming it, you know, when you look at like an API of APIs today, very complex, you know, high-level languages and all of the different functions that you have, not to mention all the different libraries, everything you'd have to know to understand something like Java or C can be overwhelming. But for this, there's only 56 different opcodes, and they're all pretty simple. They're basically followed by data, arguments, or parameters. So it's basically you have an opcode, and it does an operation on an operand. So you have load into, like LDA, we'll see in a moment, is load into the accumulator, followed by number. So you're taking a number and you're loading it into a memory location. Another one would be STA, store into the accumulator. You're then taking a number and storing it. So back and forth, it's very low-level kind of input-output type operations that are done, but it's chaining these together, creating possibly macros, but at least understanding how you can use them to make loops and other things that look more like modern programming languages that you really can make more complex software. And of course, software was very complex back then. So I don't want to make it sound like everything was just really simple. Everyone's played retro video games that are, you know, are beautiful looking, they sound great, they're challenging, they're fully, you know, featured games. And again, the assembler then translates these opcodes into machine language instructions. And the one thing you want to remember about assembly language programming is that it's specific to a particular computer architecture. So again, you use 6502 assembly programming language to program for the Nintendo, the Commodore, the Atari, because they have that chip there. It's not like Java, where if you think about today, Java is portable, right? You can write something in Java, and it should run, no guarantee of speed, on many different modern computers. And that's good because it's portable and it's easy to use. But if you write something for 6502 and 6502 assembly, you can't use that on, you know, an x86 processor. It's a different type of assembly language. So that's one thing you want to know is that if you're ever interested in programming at a low level, the 6502 I think is a great one because there are tons of different computers and video games that use it, but you are tied to that specific computer architecture. So here's an example. Like I was saying over here, this is actually the code that you may see if you're programming here. And this is an example of something pulled from an NES or a Nintendo routine here. So you can see here we load into the accumulator this number 3F, which is hexadecimal. The dollar sign is a prefix for hex. That pound sign means that it's a number and not a memory location. And then we store it here. We load another number and we store it here. So these are locations. Like we said, the 6502, if we look back, it has a 16-bit address bus right there. So these are 16-bit addresses here. They're twice this. But again, since it's an 8-bit computer, we're doing things one step at a time. So what we really want to do is take this address, 3F00, and load it into this register here. But to do that, we have to do it in pieces. So again, that's today, if you're using software, you rarely think about, if you're writing software, you rarely think about, you know, running out of space and trying to represent numbers. But this is a very common occurrence back then, using 8-bit numbers, because you can only go up to 256. And again, these are the opcodes over here that I spoke of here. And again, this is very low level, right? It doesn't look like English that much. Like you look at this, you might guess that LD is load or SD is store, but it's not something like Java or C where you have functions that may be more descriptive. And if we go over to the left here, we'll see A93F. Well, this is the same code, but written in hex. And if we notice there, A9 appears there and appears here, because A9 is the hexadecimal representation of this opcode, 3A. And then here we see 3F and 00. Those are the numbers, 3F and 00. So we can kind of see how this translates. And one interesting thing you'll notice here is that we have 8D and 8D. Well, we can say, okay, STA and STA, that's that representation. And last we see 2006 and 2006. we notice they're represented here backwards. And again, you have to load it 1 byte at a time. So we're storing it, we're storing, it's a 16-bit address, but it is only an 8-bit values here, so that's why it's separated twice. It's also in reverse order because the NES is, I always flip this around, it's little endian, right? Andrew again? Yes, I keep asking Andrew. It is little endian, right? Yeah. Yes, good. It's little endian. So you put there's the low byte and high byte, and you have to store them in this reverse order. And if we go down and we break it down to one of these opcodes, right? LDA 3F, we go here to this is what the A9 3F is, and then we can take this just one step down, and there we are, machine language, zeros and ones, you see jokes about it, but when you're using a Nintendo, you're only like 2 steps away from that. And that is one thing you always want to keep in mind, is that when you are programming for low-level computers, it is low-level for a reason, right? I couldn't imagine the amount of hops you need to go in something like Java or C. There are more steps involved in breaking it down to machine language. Here, you are barely above that. So again, this is just an example of the code. So this is the code. This is the type of code that when I write software for the Nintendo, or people historically have written stuff for any number of things, the Atari, the Commodore, this is what they're looking at. There are things you can do. There are labels to make it easier now on modern computers, but back then, this is kind of what you'd be doing. All right. We're going to look at some code in a moment, but first I'm just going to go through 3 consoles and talk a little bit about each one of them. The code we're going to look at today is graphics code. That's kind of my specialty, more than the sound end of things. So I'm going to talk about 3 consoles, and if you've ever played any of these, some of this might be illuminating. If you haven't played these but have seen them, it should still be interesting because what they were working with is pretty amazing. So in '77, you had the first, the Atari 2600 first came out in the United States. And this had a 6507, it was a modified 6502, and it was actually a cost-reduced model of the 6502, so it was even more lacking than the NES. And they were trying to save money. I think it was 28-pin, and they tried to save money. It was able to address less memory. I think it was only 4K. And they were like, at the time they didn't think that anybody would ever need more than 4K of memory. So, and they also had the TIA, the television interface adapter. So very few chips here required for really putting things on the screen. The resolution is roughly 160 by 192. And that could vary depending on the way you write the kernel. And that's the interesting thing here, is that if you've ever read Racing the Beam, it's a book about the Atari 2600. It's a great read. And they'll explain in detail about how you literally have to hold the hand of the raster beam as it's drawing the screen. So again, older TVs, CRTs, the big tubes, they would scan line by line and draw the screen from the top down, left to right over. And on the Atari 2600, you had to program that yourself. So you have to make sure you know where that raster beam is when it's drawing at any given time. And that plays into how the resolution goes, because you can divide it by a certain clock speed to have finer or wider resolution. But roughly 160 by 192. This is if we're thinking in terms of pixels. And I'm sure you know that even the oldest iPad is 1024 by 768, so much, much larger. It had 2 player sprites, 1 ball sprite, 2 missiles, and the play field. So they had baked-in amount of movement of characters you could move. So the player sprites, you and player 1 and player 2. Each of you had 1 ball that was the same color as your character that you could bounce back and forth. 1 ball that you could bounce back and forth, like Pong. It also had 2 missiles, 1 for each character. That's why in so many games there was just you shooting a gun at another person shooting a gun. And the play field, which was the background. And one interesting thing to note for programmers here, it did actually have pixel-perfect collision detection built in. Which, if you've ever played the game E.T., you'll realize that. Because if your head even touches one of those damn holes, you fall into it. And that's because they weren't actually writing their own collision detection engines. They were just using the pixel-perfect, literally bit-for-bit collision detection that was there. So once your character touched something else, there was a flag raised, and then you can do something. And the programmers of that game chose to throw you in a hole over and over and over again. So, and interestingly enough, I read the other day that people have actually corrected that in the game. There's a group of 2,600 programmers that went through and they fixed the game so that way it's more playable. And they actually had to do things like take some of the detail out of how some of the characters display in order to do that because of so little space on the actual ROM. There's not much memory available. But again, very rudimentary graphics. That's why you have capabilities, which why you have relatively simple games. But it did have a huge palette of 128 colors. So it was able to produce those nice Activision gradient skylines. So this is Atari 2600 in 1977. In 82, you had this, the Commodore 64. Not many people here in America might have had one of these. I feel like everybody I ever know that grew up in Europe had one, though. And this uses 6510, and this is a modified version of the 6502 again. And it gave more, it allowed for more input-output, because it had disk drives here, you had different peripherals. And it had a resolution of 320 by 200 and high-resolution bitmap mode. There were different graphics modes. So you can see here, same underlying 6502, but we're coming up here with a better resolution. This had background. It had 8 hardware sprites, so 8 movable characters on the screen. But this could be exploited, so you could actually have them per scan line, so you could have almost infinite amount of movable objects. It also had scrolling, so you could move the background, and it had this beautiful thing called a raster interrupt, where you would know where you were on the screen at any given time. And that sounds insane, but if you nowadays, if you're a programmer, because you can say, okay, well, if I want something to happen, I want it to happen at line 30. Of course you do. You want it to happen at like X 30, Y 50. You place everything where you want it. Well, again, here you're actually, the screen is drawing at a certain speed. If you want to stop the drawing and do something else while it's rendering, you have to know where you are. And this interrupt allowed you to time events in a way that was not possible with the Atari unless you were literally counting clock cycles of the 2600 to know where you were on the screen. So this was a huge thing. It allowed for a lot of special effects and other things that happen. But my big problem with the Commodore is that it only has 16 colors, and I think they are an awful, awful 16 colors. And there's Europeans who would probably shoot me for saying that.
Pretty terrible.
You agree that's terrible, or that I'm terrible?
The colors are horrible.
Yeah, the colors are horrible. I wasn't sure, but yeah, I mean, no, because some people defend it, but I can't understand why with only 16 colors. I don't know, they chose those. So, 1985, you had the Nintendo. And this is, this image looks much larger than the other ones. Besides that, it used a 2A03, a Rico chip. So this is a kind of a chip produced not by the original company, but like a second source chip. Had a 2A03, had a 6502 core, and it had a picture processing unit, another chip to help draw all of the graphics on the screen. It had a 256 by 240 resolution. It had 64 sprites, so a lot of moving images. That's why if you play Nintendo games, if you've ever played Nintendo games, there can be a lot of motion of characters on screen at once, with bullets or enemies, many things. Had backgrounds, you could scroll the backgrounds, and it had 64 colors. And again, whenever I'm mentioning palettes, most of these machines can't, most machines can't just have all colors on screen at one time. So the NES has a limited number of colors that you can show. But this is Nintendo in 1985. It's one I'm most familiar with, and I'm going to show you some example code from this in a couple minutes. And oh, yes, right now, actually. This is the hands-on graphics demo. If you have a Windows or OS X computer, I've included a little demo, and it includes an emulator, a batch file, or a shell script. So if you're using Windows, there's a batch file. If you're using OS X, there's a shell script. There's an assembler and some code. So I'll show these folders because this is kind of, even if you're not, if you don't have a computer now, you can grab it later. And even if you don't have one now, you can look at kind of what goes into developing something. There is Wi-Fi here. It's Game Center, and it's Game Center is the name of the SSID.
That's Game Lab.
Game Lab even, and sorry, and it's Pac-Man Fever all lowercase. Okay. So again, and you can just go to tinyurl.com/6502 demo. Somehow that tiny URL wasn't taken, which is good. All right, I'll leave this up here for just a second. Maybe I can just write it over here where nobody can see. And I don't even know why I'm doing that. So yeah, it's tinyurl. .com 6502 demo. All right, and again, it's Game Lab and Pac-Man Fever for the password here. So let me take a look at this. This isn't what my desktop usually looks like, I promise. Shift the projector. So when you unzip it, you're going to see something like this, Mac and Win. I'm just going to go through. They're almost identical here. There's an emulator and folder that says Nestopia on each one. But we'll look at the Mac one for now. ASM6 is the assembler. So this is a assembler that is used to take the code, as we said, and compile it into something that can be ran on the Nintendo Entertainment System. And since we don't have a Nintendo handy or all the hardware needed to get that software there, we have Nestopia, which is an emulator. And I should make sure everybody's familiar with that. Emulators are software programs run on modern computers that emulate the hardware of older computers, so that way you can play that software on a modern machine. So all the games you wanted to play growing up, you can play them again. If you want to make new software for those older computers, you can do that. So they have emulators just about for anything you can imagine. So again, there's one in each folder here, Nestopia, and there's some assembly code. So taking a look here at the demo. Is that readable? That's not really readable. Make it larger probably, if I can figure out how. Font. Oh, there we go. Is that almost readable? I think. Okay. So this is the demo ASM, and I'm not going to go through all this in great detail, but there's some things that you can learn from looking at some source code with even just a few comments that explain things about how NES software or 6502 software in general has to be handled. So one interesting thing is that if you ever write software, now you're writing software most likely on a computer that already has an operating system. And you don't usually think of that because most computers you've ever encountered have operating systems. And you're like, oh, great, well, I'm just writing some software and I'm going to run it. And then when you're done, you stop it. Well, on a Nintendo, you are putting in a cartridge, and that cartridge has your program on it. It has all the graphics on it. It has all the code for all the sound. And when you put that cartridge in Nintendo, push it down and hit the power button, the hardware is just looking for that software on that cartridge at specific locations and executing it. So there's no operating system. So you have to do a lot of things when you're writing software for older computers that you don't have to think about and when you're writing software for modern computers. We do have some things that are similar. We don't use any variables here, but I put one in. So you can still declare variables here in the code. This is an actual header file, but this is not necessarily needed. This is only needed for the emulator itself. So the real code starts here. You'll notice I do have some English, like reset and clear memory. And if you're not a coder, these are just labels. So these aren't things that the computer actually knows. So I wasn't lying to you earlier and trying to make it seem like it's harder than it is. It is really hard. But you can put in labels like clear memory, reset, etc. And these labels are more for your benefit than the computer's. And here's the reset routine. And what you're doing right away here is turning on or off some different modes. And these first three lines right here, this is something you don't think of when you're writing your own software. LDX 00. So I'm saying I'm loading into a memory location the number 0. And then I'm writing it, I'm SDX, I'm storing X in 2000 and 2001. And these two memory locations have to do with the status of the screen. So the first thing you do when you reset the Nintendo is turn off the screen. And you're actually responsible for doing that. The reason you want to do that is because when you start that up, depending on how you pulled the cartridge out the last time and if you left the power on and you stuck the other one in there or any other things, there could be garbage on the screen, there could be junk on the screen. You don't know the status of what's happening, and that's the thing about assembly. You don't ever make any assumptions. You just do everything you can because nothing is done for you. So this is the first step, and the next step is going through, this is a loop here, going through and storing all of the, storing the number 0 in every single memory location. I won't get into the loop, but then what you want to do through is go through literally and zero out all of the RAM that you have available to you. Again, because you don't know what is stored in those because of random, random things that could be there at startup. Right, and then after that, there's a warm-up routine, and again, we'll just go through kind of the setup of this. The warm-up, you have this warm-up routine. Most of the warm-up routines out there were based on some people that reverse engineered a duck hunt warm-up routine and didn't really realize why you had to do things the way they did. And I think there have been more people that have figured this out. But this kind of standard warm-up routine of waiting for a few cycles for the machine's hardware to be ready was found, by analyzing older software. So again, the first thing we do is we warm up, we load the palette, so we're literally setting all the colors. Then we're clearing all of the screen data to make sure nothing is on the screen. And of course, you remember the screen is off all this time. So that's the first step. You turn the screen off, then you can do everything you want. And this isn't taking minutes. This is taking no time at all. So you don't want to think this is like a long process. But you want to make sure the screen is off. After you've loaded the palette, you've cleared the screens, then you set up the first picture to be loaded, and then you load the first screen that you're going to see, and then you go down to this part here, where you're actually turning on the screen. And again, here, remember before I wrote 00 to 2000 and 2001? Well, here I'm writing these binary numbers to 2000 and 2001, where I'm turning on the screen. And you might think, well, why are you going here from hex, where it's just 00? Why do you break it out here to binary? Well, every bit is useful in different ways in low-level hardware programming. And here what you're actually doing is using a different 1 or different 0 in a certain location turns on or off different settings for the screen. So depending on the way you want the screen set up, you write a string of binary data. So it's not like I want my screen to be 640 by 480 and I want to have the background color this color. No, you literally need to know these strings and what's a 1 or what's a 0, what's it going to do in that location when turning on the screen. Yeah, so again, and then after we've done this, we've drawn the screen, we've turned it on, then there's this infinite loop, and this loop happens, but then once a redraw, you jump down to this part, but we have no logic here either. So this is a pretty boring program, but basically what it does is it goes through, turns it on, warms it up, clears memory, loads a picture, displays that picture, and then displays that picture infinitely. So it's a very simple program, but it will run on a real Nintendo if you were to compile this and put it on, put it on chips and put those chips on a board and put that board in a cartridge and put it in your Nintendo. But luckily, we don't have to go through that process now. We can just use emulators to do that. And right here we have a couple of different pictures loaded. And I don't know how much time we have to go into this. A few more minutes? Cool. 5:10? Perfect. So, well, again, just a high-level kind of glossing over of this, and I'll show you how to compile it in a minute. There's some different things that go into displaying that picture. There's one thing here, this file, go.chr. This is actually, CHR is short for character graphics. This is all the tiles that we have ready to draw on the screen. And older computers, like the Commodore and the Nintendo, you couldn't draw pixel for pixel drawing, or you could in some ways, but the majority of the images were loaded from tiles. And that's why, there's those famous stories like Mario Brothers 1, for instance, that the cloud that you see is the same as the bush, except the bush is green and the cloud is white. It's the exact same thing. Like, why the hell wouldn't they just draw a bush and they already have, why would they just do that? Well, they're trying to save space and it's all tiles, so they reuse it. That's the same reason why you have green turtles and then you have red turtles in Mario Brothers, right? What's the difference? Well, they're two different enemies. They act different. Yes, they act different, but they use the exact same tiles but different colors. This is all ways to save space. So again, this file has our character graphics in it. This PAL file is a bunch of colors that I chose, and then this .nam, rhino.nam, is actually a map of the tiles. So you want to think of it, every image that is displayed on the screen has three parts. It has the tiles that you're going to use, it has that map of the tiles, like where you're going to place those tiles. You want to think of it almost as like a mosaic, and then what color are those tiles going to be? All right. So there's a great online tool that was created by some people here actually. Sarah and Andrew worked on this, and this is worked on for Playpower. And this is actually in Flash and runs. Oh, that is full screen. Perfect. And this, as you can see, if you go to this address, educator.com/pine, it'll run. It stands for Playpower Integrated NES Editor. There's this Submit to Dev Library button that doesn't do anything as much as you click it. I just want to let you know. There's no dev library that you're filling with your ideas over and over again. But it's nonetheless, it's fun to click. So here you can see everything. This is that CHR tile, right? These are all the tiles that make up this screen. Here is the palette, and you can see, oh, wow, yeah, this is definitely the palette here. This is what I was talking about. This is the cloud, right? It's just a bush. I feel bad saying that because sometimes I blow people's minds with that fact, and it could be a big day for nerds. So these are the tiles here. This is, again, the tile map, right, where everything's placed, and this is the palette. Like I said, these are the 3 steps. It would have been great if I explained that, why I had this example up. And if you want to, you can load some of the things in that demo folder I gave you and modify them. And one interesting thing about that is because you can see how everything actually acts independently. So if we open the palette, first of all, in here, geo.pal, now the colors change, right? Because we've loaded a new palette. And then the next thing we can open is the character graphics. And if we open this up, geo.chr, we're going to go back to this one. There, now you see it looks almost recognizable. Why is that, right? Well, now we have all new tiles, and we have an all new palette, but the map is still in the same place. It's kind of like those puzzles, I can't remember what they're called in newspapers, cryptograms, I think, cryptograms? Kind of like cryptograms, where everything it's all representative of something. So, you know, anywhere you have $sign here, it's linked to this character right here, and this could be different in the other CHR, so it shows up separately. The last thing we can open here is the name table file, which literally is that map. And if we open this up, this is the image that is going to show, if you compile, this is that image that you're going to see on screen. And again, Color Caves is another cartridge I did with a friend, Alex Maurer, who did the music and the art. And I like this example because this is another great example, I think, of what you can do. He has a really minimal style of art, but he made this image only of these characters here, and he drew all of these as well. He came up with all of these. This is an early tile set that he thought he could draw a bunch of art with. And I really love the fact that he made this darker, and there's that implied like negative space, all with the curve. So he's kind of, and his art is much more complex than this, but again, this is a simple picture here. And if you want to use this editor, you can go ahead and just mess this up and do something like this, and you can see that the palette changes as well. We won't go into that, but you can save all of these individually. So you can save all of these pieces out, and if you save all of these pieces into this folder, like the character graphics, the palette, and this rhino.nam, you can compile it, and it will compile. Let me see here. Bet I didn't have anything embarrassing. I don't know what I would have embarrassing on my terminal. If it's possible to have something embarrassing on your terminal. That's always a fear of mine when I'm doing something. I'm like, oh, web browser is much more embarrassing than terminal. So anyway, so here I'm in this folder, and then you can just do compile.sh. No, I'm in the wrong folder maybe. Oh, Mac. There we go. Compile.sh, and you can see it goes past 1, past 2. It's made this. And it's also made a list file, which I'll talk about briefly right before we move on to something else. So here we have Nestopia, hopefully. I don't understand how there's still shareware today, but apparently there is. Okay.
Shareware forever.
I don't know. A quick start. Cancel. There we go. Just, so again, that compiled NES file looks like this. It's not going to be too much. It's got to look just like that because, like I said, it just loads one screen. But again, you can play around with this and edit those graphics and save them if you're a little bit savvy, and compile your own ROM in this way. So I just wanted to show you a little bit about, to get an understanding across really that at a low level, everything is made up of a bunch of different components that need to work in harmony in the right way. And you also want to remember, if you're ever programming for a low level, you have to do a lot of that work. So you have to make sure you have all of your files straight. And more than that, you have to make sure you're clearing the RAM, setting up everything properly, because there aren't as many fail-safes. A lot of what happens in older hardware will happen the right way or the wrong way, wherever you code it. There's not going to be, there aren't really as much debugging that goes on. The last thing I wanted to show is this demo list. This is really interesting, and, well, I think so. demo list is a file that is also put out by the compiler here. And you can see that this is the code that I was showing you earlier. And over here, this is where I got that screenshot. You can see all of the hexadecimal on the side. And one interesting thing here is that to note is that 8000 is the memory location where it looks when you boot your Nintendo, where it looks here, or where the cartridge memory starts. And here is where it resets. You'll notice this 8000 goes up to 8001, then 8002, 4, 7, and it goes up in 1 byte. Every time a byte of data, it goes up to the next one. And if it goes 2, then it goes up 2. If there are 3 bytes, then it goes up 3, and it's hex, so you get into A through F. But over here we have the program counter. So if you actually want to look at the code, you can see the code you type. You can see all of the hex, and you can actually see where you are in the programs in the program counter, and that changes as you go through. So this is one interesting thing about the assembler is that you can actually see where everything is actually happening at that low level to down to the very byte. All right, so that was about the end of the tech stuff here. I do have one more picture that I really like. Some of you may have seen this before. This is from Futurama, and I guess one of the creators actually grew up using the 6502. So this is the part where they X-ray Bender, and he has
the writers are nerds.
The writers are nerds, definitely. This is where they X-ray his head, and he is powered by one. So thank you very much for listening.
Okay, questions. So I had a C64.
Yes.
Right, so I grew up in Germany. I'm one of those people.
Yeah.
I'm one of those people that when they play V,
yeah.
they actually, I like it.
Yeah.
Right? I don't like, why did Terry use those weird colors?
Yeah.
I'm like, oh yeah, I know. He's actually using the exact color palette from the Commodore 64. Have you ever played Shadow Mario?
No.
Have you, so I mean, the things like when you show those ROM hacks, the first thing I think of is people who did ROM hacks.
Yeah.
And a lot of them are just like, hey, look, Mario's still really cool if it's just blocks. Like, they'll just replace everything with squares, and like regular Mario is a square, and Super Mario is like 2 squares high. And because the physics are great, it still feels like Mario.
Yeah.
No, Shadow Mario is like they took the shrubs and Mario and the enemies, actually not Mario, but everything, and just turned it like a single color. So as soon as the enemies like overlap with the shrubs, they're basically hidden from you. So it changes the dynamic absolutely radically. So the thing that I'm going to start off on right now is you explained a lot of this programming stuff and a lot of the assembly stuff, and my background in that is like forever ago, like with the Commodore 64. So I don't do it much anymore. In fact, I always thought it was a godsend that I got the higher level, more abstract languages, which is interesting that you bring that up because abstraction. You're abstracting from the machine. You're actually going closer to language. Yeah. Right. So it's like that's an interesting construct. But so when you learn this now, or when you teach people this, I'm assuming there are copious amounts of things online that you can get into. Donna Bailey was here 2 weeks ago, and she described what it was like at Atari in the early '80s, where there was nothing. Yeah. There was, in fact, infighting in the company. It was like well-kept secrets because that's how you got better salaries. Yeah. Right. So would you, and I know you're an educator, would you recommend to people who want to get a grasp on machines and digital literacy that that should be a starting point in light of the internet and all the information that we have nowadays? Yeah, I don't know if it should be a starting I don't know if it would be a good starting point, but I think it's a good exercise. So you knew how to code in, let's say, C or Java or something before you started? No, that's why I said it wouldn't be necessarily a good exercise. So I started, like I said, I started the No Carrier project around 2006 as the first gig, but like for a couple years leading up to that, I was learning how to program. And let's backtrack a little. I started going to chip music shows. If anybody's familiar here, it's music made with older video game and computer hardware. I would go to shows and I saw people doing video, and it wasn't what I wanted to see, basically. So I was like, well, I want to see people doing video with older video game and computer hardware.
but nobody was really doing it, so I thought I would do it, and I didn't know how hard it would be when I set out to do it, but it was something I was really motivated to do. So I taught myself to program starting with 6502 assembly. So that's why it can be challenging sometimes to do these talks, because a lot of the terminology I didn't have straight for years, and I probably still don't have straight, because you're learning it. And once something happened, I was so excited, I didn't care about why it was working. I was just going on to the next thing to get it working. So then I went back to higher level languages later, and a lot of what was happening, it definitely informs the way I think of programming now when I look at higher level languages. And I think it's a great exercise for people that are programmers to look at lower level languages, but I don't know if it's always an ideal starting point. I had a very specific goal in mind, and I needed to learn it to achieve that goal. And for that reason, I think it was motivating for me.
Well, you're not coming at it from a computer science, like you didn't study computer science. You learned this specific tool. So what's your experience now have you exposed yourself to higher level languages? Have you tried to get into?
Yeah, I mean, I've done C and Java, and I primarily code in relation to computer graphics and the video, and I've done some 3D stuff as well. But I guess it's always been kind of an exploration from a perspective of what I want to do, artistically. Like I want to have this look like this. I'm like, well, how can I do that? What are my options? So I've always kind of been led through different languages and different frameworks based on what was possible with them and what I wanted to do. That sounds strange, but
no, not at all. So you feel like So I mean, this leads me to my next question. So you seem to be interested in this because it allows you to be as close to the hardware as you can.
Yeah, and that I think is one interesting thing of it is that one interesting thing about it is that the more of course I've programmed a little bit in high school. I had like very rudimentary classes, but not an entire class. And I've seen code on the internet before I started. I don't want to make it sound like I just looked at 6502 for the first time ever. But
assuming you had resources, like I'm assuming there was already something on the internet.
There's a development community, a Nintendo development community that is they're pretty active, but they're very kind of insular, and they were a little strange. That's why, as an educator, I was always like, well, I want to make sure I release open source software, and that's the reason I did that. It's because like once I learned, I want to teach other people how to do this, because there weren't as many resources, and there are more resources now, 6 or 7 years later. But at first, there weren't really as many as there are now. But I guess going back. Yeah, I think being close to the hardware is really important for me because I know exactly what I can and cannot do, and I enjoy that aspect of it. And when there is something that I know can be done, it's challenging to figure out how to do it, given what's available.
Okay.
And sometimes I sit down in higher level languages, and where I know it well, like if I'm using processing to do graphics, or I'm using something even like jitter. In any type of environment, I know I sit down, I'm going to write some new software for, visual performance. I'm like, what am I going to do? I'm like, I can do anything, but sometimes I don't know what I want to do.
So it's good if you have less possibilities.
Sometimes it can be good because I'm like, oh, well, I know I have these possibilities. I know that these are kind of the tools, this is kind of on my palette right now, and I think about what I can do with those, and that informs a lot of decisions I make when writing software.
Sounds like a comparison of chess to a miniatures war game, almost.
Yeah.
So I mean, that's interesting because essentially, like nowadays, if you do any kind of graphics programming, you have like numerous off-screen render buffers.
Yeah.
Right? So you can basically, whatever resolution you're running in, you have that resolution multiple times over in graphics memory, and you describe briefly how that tile set looks. As far as I remember from the class I took that you taught in 2010, that tile set is smaller than the screen resolution, right?
Exactly.
So that's an imposed constraint by the specifics of the NES architecture. That's not a 6502 specific.
No. So for the Nintendo, for instance, you have to use those tiles to make up the graphics that you're going to do. You don't have like that, those tiles that I showed on the screen, you can't just take those tiles and arrange them into a picture and then throw that onto the screen like you can nowadays. So you can't, say if you want to start out with an image of something, you have to build that image up from its component parts and tiles. So that definitely informs the way that in the limitations that you have of character data, of the amount of tiles, what are you going to draw, right? What resolution is that going to be? Because if you can only draw an 8 pixel by 8 pixel tile, then is that going to be your building block? Is everything going to be based on 8 by 8 pixels? If you're going to go smaller, then that's why you saw in that one character graphics, there were some like angles there. You know, like an angle one way can be used. If you rotate it, it can be used to draw something else. So you have to start thinking of limitations there.
I actually thought the image that you showed from Alex Maurer is a really good instance of like more than the sum of its parts.
Yeah.
Right. He uses very few shapes. It's pretty incredible what how much mileage he gets out of that.
Yeah, and not the shapes and also palettes. You know, palettes are something you also have at your disposal, which sounds strange because you're like, of course, anything can be any color I want it. But if you only have roughly 16 colors that you can show on the screen at one time, and one of them has to be like this a background color, so you really are down to like 12 colors because of the way the palettes repeat. You have to make very clear choices about how. You got to make very clear choices about the palettes you use and the tiles you use and how you blend them together to represent an image.
Well, the interesting thing that I thought about while you were talking about that is like nowadays, rasterizers, which are the pieces of software that do all the pixel painting, they're programmable, but they're like the most hidden secret of every graphics vendor, right? And you're basically describing a time where not only was the rasterizer something you did, but you also had like influence over every position that the beam could be at.
Yeah.
Right. Like now, I think id Software submitted an extension to OpenGL that allows them to interrupt the tearing, so that they can do VSync.
Yes.
But VSync when the beam is like not in the middle, so it's not disturbing to you. So that was like an extension to OpenGL that they submitted. This was like back then you would have just had all that at your fingertips.
Yeah, exactly.
Which is like, amazing.
Like Atari, for instance, if you start drawing a picture and you stop, it just draws that line for the rest of the screen.
Yeah, because like, was it called a line buffer? Like, because I think no. You stored like what a line would draw in memory, or did you have to constantly? Was that like a single register? You had to update.
There was like 4 different registers, and you were taking data. If you were drawing the playfield, you were drawing the playfield. You were drawing the playfield from stored in memory, but you had to draw it every time the screen rendered. So once the screen draws in the Atari, once you draw it, you can't just draw it once like we saw on the Nintendo there. It doesn't just stick. On the Atari, you had to continue to draw it again and again and again and again. And that might not sound like a chore. You're like, oh, just set a loop to do that. Well, in that program code, you also have to think about everything else you're doing, like the player's movements, all of the game logic, everything. So everything is happening kind of simultaneously, timed to the graphics drawing.
So that leads me to my next mild topic, which is basically something I always bring up here, which is tools. Tools, or essentially whatever it is you use for your art. Right? My canonical example for someone who does something like you is Ansel Adams, right? Like obsessed with a camera, like knew everything about a camera, wrote books on camera technology, made his own cameras. Right? I guess you're not making your own. Well, maybe you are kind of. We'll get to that in a second with the glitchiness. But yeah, I mean, the thing is there, like nowadays we have all these tools like Unity and different like APIs and whatnot to do things, and there's like most of the times people that don't know the low-level stuff, there's a danger to be biased by the tool that they're using, right? But at least in that sense, they're trying to make it something that would make a game or would make X. Mm-hmm. You said that some of the considerations for the hardware back then were clearly motivated by cost saving. Mm-hmm. Right? So how do you feel about you repurposing something for your artistic constraints that had very different constraints in reality? Like, how does that change how you like your process or how you think about it? Or is it like doesn't really matter? It's just an interesting constraint. But
yeah,
like I guess what I'm asking is like, how do you feel about the kind of arbitrariness of the constraint?
Yeah, I mean,
like not self-chosen. You didn't decide that these would be the constraints for your artwork.
Yeah, I mean, sometimes I guess. Yeah, I don't know. Like I said, I'm pretty objective when I approach it the first time. So I'm like, all right, this is what I want to do, and what do I have available to do it, right? And I guess I still come at it that way. Like in that one, clip that I showed of my real-time video stuff, I tend to do a lot of strobing, kind of almost like low-resolution psychedelic graphics, and it's something that I came to out of performing, and it kind of changed. Where in the beginning I was doing more graphics that were like that used some of kind of the that when you looked in the beginning, you'd like, oh, this is a Nintendo because of this palette or of these tiles or of this look. They may have been influenced more by gaming, and then that kind of slowly deteriorated into just kind of exposing what I can do by pushing the hardware a little bit. So it's not that I really thought of it that much, but as you learn more about it, I guess as you learn more about what some of the limitations are, it allows you to make more informed decisions about how far you can push it. Sorry, meandering.
Yeah, it's interesting. I mean, my views, of course, and you mentioned this, is that you were trying to do the visuals on the same hardware that the musicians were using for their work.
Well, yeah, I think that's an interesting part of it. I mean, I've done visuals for all different types of events. And I've used Nintendos in strange places. Like I remember I lived in Philadelphia before, and I did a couple like industrial goth parties, and I was using like Nintendos. And I was like, man, I wonder how this is going to go over. But it does go over well. Because again, there I was doing strobing, kind of psychedelic light show style stuff. But I did really get into it the first time because I wanted to kind of complete that experience. You hear the music, and you know the music maybe, or the sounds, where they're coming from, and I wanted to kind of have that same experience with the visuals. Well, hearing that music, what does it make you think of? How does that kind of synesthetic link be? How can you complete it? And I think it's from having graphics that representative of that same feel.
Interesting. Leads me directly. You're basically making this so easy right now.
Well, that's good.
Everything I have here is leading naturally into it, because the things that you showed here in your presentation are kind of static. Like they're inherently like you're showing an image and it is composed, and here's how you set up the screen. Blah, blah. But your performance when you work with chiptunes artists, because you VJ for the shows, feels to me more like, just from watching it, seems like Jeremiah in Null Sleep is fully immersed in the moment, and you're very concentrated. Yeah. And I was always like, and now I get the chance to ask this question, I was wondering whether, when you're doing that, are you sequencing parts? Because, and you actually did allude to it slightly in your talk on how you have 3 NESs set up, or are you also in real time tweaking parameters of what's going on each individual system?
Yeah, well, that definitely changed over time. And the best thing about using older computer and video game hardware is that you have controllers that are made to be held in your hand and are made to be manipulated. So it's really great, because I would never want to VJ with a laptop, because the precision of hitting one key, and what if I hit the wrong key? It's dark, I'm drinking. And I've held a Nintendo controller for 20 plus years of my life. I know what the buttons are and how they feel. So strangely enough, it does lend itself well to performing live. But again, using 3 Nintendos, that's 6 controllers, right? So usually what I have is 6 controllers laid out, and I have 2 Nintendos any one-time mix. So when you see the performances, there's usually 2 layers, multiple layers of graphics on each machine, but 2 layers actually mix to a video mixer, and the third one I'm queuing up new software. So it's kind of like a DJ. If you ever see a DJ mix, they have a headphone and they're always listening to the next track that's going to be coming in. That's part of the queuing process. So I have 2 Nintendos showing graphics, another one I'm loading software, and usually I'm one-handed loading software by maybe manipulating another piece of software with the other hand. And that way, when there's going to be a change in music, maybe a new song or a new part of the same song, like I know there's a big change coming. I work with Jeremiah Johnson Nolsleep, this artist from New York, frequently. I know songs. I'm like, okay, this part's going to be coming up. And I envision, what kind of graphics do I want there? If I have 2 mixed in, when the song changes, when it goes from, there's a big build-up and then it drops, that's when you throw in a new piece of software. And so there is that thing of loading software that has to be done and manipulating software, and that's just part of the juggling. And then within it, I write software so I can change the speed of the animations, the colors that you see, the patterns that you see, and then there's the video mixer, which is compositing them. So it really is kind of a concentrated thing. I do kind of concentrate, and I like working with people, chip musicians that do a lot of live manipulation, because I can watch them. It's the same thing with bands. It's even more fun working with bands, because then you see the drummer and he puts his hands up, right? And his hands are going to come back down. And when they do, that's when you want to make a change in the software that manipulates in some way. So there's a big change on the screen. So for me, It's having the graphic and the sound linked, and doing that is a combination again of always loading new software while manipulating the other software live, and really kind of going back and forth with the performer either ahead of time or in real time, trying to anticipate the changes.
How much of that is improv and how much is rehearsal?
It depends.
Do you rehearse with your?
I never really rehearse, but sometimes I'll look over sets, but that's still only for people I know really well.
So it feels
the majority of it's improv. And I've DJ'd for a long time, so I think it's given me a good understanding of kind of song structure and changes, and as long as people aren't all over the place with the way they play, as long as it's not super experimental, you can kind of anticipate changes enough to keep things synced. And that's a big part of what I like to do. I remember once we were doing a book festival somewhere in Europe. We were in Europe, and some guy came up to me and broke in English afterwards, and he explained to me that I wasn't his favorite DJ. Which was nice. It was a great way to start a conversation. I was like, thanks. He was like, but like your timing was like impeccable, and I was like, thanks. And he was like, how were you timing it all? What were you syncing it with? And I was like, yes, this is the type of compliment that I'm looking for, because that's like really what I'm not always worried about. What people remember, and that's why I've kind of come to more low-res, more abstract, more psychedelic, more black and white strobing, because I realize that it's not what I want people to remember what they see on the screen, but it's the feeling of the synced music and the synced video and the whole kind of experience. And that's kind of where I moved.
I have like 20 more things here, and we're already over an hour into this, so maybe I'll still get to the glitch stuff later. Okay. And that's what I'm really interested in that. But I'm gonna first open it to the audience so that we can get some questions. So before you start asking your question, please wait till Widget comes around with the microphone, because this is being taped. We'd like to have all your contributions.
Alan O'Carrier. This is a question about the assembler for the NES. I actually am an NYU alumnus. I graduated in 2008 with a BAS in linguistics, but I almost got a double major in computer science, and I have taken C++. I'm not familiar with garbage collection, and I noticed that. So I think with a much lower level language like assembly, there's like tons of that. And I know that with garbage collection, like you do not want to leave garbage in system memory, because you would then have to get a systems analyst to find that piece in the ether and clean it up. What happens if you accidentally leave a piece of garbage in the memory with assembly?
Well, that's a great question. So, people that may not be familiar with programming, garbage collection, really has to do with certain programming languages. You have to worry about this. Other things like Java, you may not have to as much. Where if memory is used or released at certain times, it's done automatically. And certain memory, if you have something stored somewhere, it could conflict with something else. And the Nintendo, I guess the short answer is a lot of older. The Nintendo, the Atari, many other machines, you don't have a lot of memory, and again, like I said at the beginning, we're clearing that memory, so you know the state of it at almost every moment. And if something goes wrong, it's usually easier to see. But it's not the same way where if you have too many variables, stored, things are going to slow down. But the big concern I've had is not properly, when I first started, is not properly understanding how storing some things in some memory locations will spill over onto others. So that's more of a problem, is that it's not going to tell you if you store something in one place and then you store something else there. So it's not going to say, oh yeah, the assembler's not going to tell you. It's just going to say, oh great, well you put one variable there, you put one number there, you're not going to put another number there too. Oh, why not? We're just going to overwrite the other, what's already there. So more of the problem, I think, is not just garbage collection, but just making sure in very lengthy programs that you know where everything is stored, and making sure that you're not, you're not like double dipping in some way.
Or overwriting it.
Okay. Overwriting program code.
Yeah.
So there's nothing that prevents you from doing that.
And I didn't even use the debug until I met other people online in real life that use debuggers for the NES. I didn't really do that because I started programming. I didn't really know what debugging was, because I was just learning on C502s. I was just being really
freaking careful. That was like what I did. That was
a tad way to learn it.
yeah. And still today, it's kind of what I think about it.
Other questions? Over here. Man with the mic around off.
I feel like I've seen a C compiler for the 6502.
Yes.
Do you just prefer assembly because like control or like any other reason?
Yeah, there have been a couple different people that have tried, and maybe some successfully even. I've never really used them, the people to use C or higher level languages to compile down for the NES. And yeah, a lot of it comes down to when you're doing graphics, especially the type of real-time graphics, you want really close control. And I've found that things like macros are very helpful at using in assembly, but I've never really tried any C compiler just because there are so many things. Like I said, like if you're turning on the screen, you're writing individual bits there. You write them, and then you're using a C compiler. It might have a thing called like turn on screen. Well, I don't know what's actually going on. It's turning on the screen, but what are the actual settings? So, I mean, I've seen those type of things, but usually when you're working with something like assembly, it's so low level that you want to have the control, and some of the things that may save time might end up actually causing you more problems later. So I'd recommend definitely macros are very useful in assemblers that support them.
So you mentioned earlier in your talk that you've done some stuff on cartridges.
Yes.
And actually, wait, was it you who gave that talk at Flipfest 11, also on the same subject?
Probably.
Yeah, I went to that talk and I was like really inspired by it and really excited. And I actually went shopping for a, I guess it's not called a flash cart, but like, yeah. And those are like really expensive.
They are.
So I've noticed a lot of people who do stuff with NES, they just do stuff on emulators simply because the cost is so prohibitive.
Totally.
I was wondering, like, what's behind your decision to use cartridges for some things and not for others?
Oh, that's an awesome question. Yeah, so that's a huge thing in chip music, a huge debate in the chip music community, and I always love huge debates in nerds communities. Like outside of that community, those are always so fun. Like that's a huge debate with 90 million. You know, the whole world is like nobody cares. But so real hard. Like, what do you do? Right, emulator is one way to go. Like you said, like we looked up there. Why not just take computers and do that there? That's one way. The cartridge that you mentioned is another way. And again, you can actually take the code and program it onto little chips, and then put those chips into cartridges that you used to play on your Nintendo and put that in. That was a method that was there. That was the only other option besides emulation for a while. But recently, a guy from California made something called the Power Pack, where it actually uses like a compact flash card, like a camera, and you put that in a Nintendo cartridge, and you can load software. That's what I use, and I have a bunch of them. And I guess the short answer is, if you, the short answer is that the quality of the video output of the original Nintendo is strikingly different than the emulator, because you have that it's 256 by 240. But if you have a black and white pixel next to each other, one is black and the other one is white, right? It's that crisp, clear output that I really enjoy, and using a video mixer as well. The video mixer takes, RCA or composite video, which the NES outputs, and it composites two images over top of each other. I often do chroma keying, kind of like the weatherman standing in front of something and the background is subtracted. I do that so that way I have a lot of black in one picture, and then I put that over top of the other one. And the nice thing about using the NES are that video output is so clear, it's not compressed, it looks crisp, and it allows for seamless mixing. So that's why I tend to use hardware. Plus, like I get gigs, far away. Like the one I showed was a gig in Tokyo. When I go there, nerds expect to see Nintendos. And
you see Famicoms?
Famicoms? No, they would actually like to see, because it's different. They have a Famicom there. We have the Nintendo, So a lot of it is about if there's such a thing as street cred, there's that too in this scene. But like I said, I prefer the original hardware, and again, the controller manipulation as well. The controllers lend themselves quite well to it, and I haven't found a really good way to do it with software yet. But there is something called OpenEMU that's a couple guys from New York wrote, and it's pretty nice. And it's for Quartz Composer. It's Mac-based.
Can you do the development on the PC Mac? Do you do most of the development on that and then just move it over to the hardware?
Yeah, I test on emulators, and then I throw the ROM images onto this compact flash cart, and then like I said, I always have 3 running at a time, and it is menu-based, so I can choose, which makes it easier. Yeah, questions?
Great, my turn. So, back to our conversation. You are a glitch artist, is that correct? You also do glitch art.
This is a really interesting topic.
Yeah, no, because I'm going to get into this now, because my view of current glitch art is mostly algorithmic.
Yeah.
Right, so all the glitch art that I'm familiar with that uses modern hardware, like modern day hardware, usually operates on the fact that many algorithms that we use are deliberately lossy, like JPEG. Right? And then if you take that slider and move it all the way down, you get these amazing boxing artifacts that are based on discretization of the JPEG compression algorithm.
Yeah.
Right? And then people like layer these effects. Like composing is a very big deal. It seems to me that you have a harder time doing that if you're being excessively precise with the hardware.
Yeah.
What does glitch art look like in process and in result on 6502 level hardware?
Well, there's a number of different people that do software and hardware glitch art on everything from Nintendos to Commodores. I don't know if there's, I think of any Atari, if I can think of any Atari stuff off the top of my head, but the process is, it can be very different for different artists. And I mean, the first person that comes to mind is someone I worked with for years, Nintendo, Jeff Donaldson, here from New York City. And he does all hardware. And he has a very interesting approach where he actually opens up the machine, and if you open up a Nintendo, the chips are actually labeled. Like you can see PPU, I talked about that, the picture processing unit, it's labeled. The RAM chips are labeled. The 6502 is labeled. And you can get the pinouts online, meaning you can see what pin on that chip, what little leg, actually has voltage coming in, voltage going out, and you can start connecting some of the RAM lines to some of the things on the PPU, and you get graphical errors. And of course, you can also, do some damage to your hardware as well. So many people use, like Jeff included, use hardware circuit bending to do it like in that way. And it's funny that you mentioned the glitch artist thing, because I wrote a piece of software years ago called Glitchness, and I wrote it because of problems. I was trying to write software that to do something I wanted, like I keep saying I always do. And unfortunately it didn't work, and I was having errors. And it had the graphics, the glitching errors that occurred on screen were very similar to what I saw in circuit bending. But also, like I said, when you were younger and your cartridges didn't work and you saw like all those graphics, and I was like, oh, that looks really cool. I used to also play around with Game Genies when I was younger and make up codes just to have the thing kind of glitch out. So I was like, wow, this is kind of interesting. I wonder if people will be interested in this. And just like I said, I released a lot of stuff open source. So I pushed out a preliminary piece of software called Glitchness, and people started using it a lot. And it's open source, and it's GPL licensed, so people actually started selling it on cartridges, which is interesting. And they all were like, "Do you want money?" And I'm like, "Nope," because I don't ever want to get into the idea of like selling things. I have to make stuff, and that's hard and time consuming, and then I have to mail things to people, and they don't get them, and that whole thing. So people started selling Glitchness, which was cool, and the interest was really high. And I had people contacting me from all over the world asking if they could use it in XYZ, and I was like, "Sure." And I sell it here, yeah. And I've made subsequent versions of it. It was kind of like a I was really shocked the other day. I was on a forum somewhere, and people were like, "I'm just getting into VJing, and I want to do like, chip visuals." And somebody was like, "Glitchness is a staple or a garret." I was like, "What?" It was like an accident when I made it, but it's cool. I don't really do a whole bunch of glitch stuff, but it's been shown in gallery shows and other places. So kind of accidentally, which is I guess the best way to become a glitch artist, is to make a mistake and then have people like it intentionally. But now I've kind of extended the software to the point where there's actually like a tap tempo function in there for the glitching. There's you can load tile sets, you can change the palette, you can speed it up, slow it down. So there's a lot of thought around this.
Do you use it yourself in your performances?
Not often. Not often. Once in a while, depending on the artist, but not often. It's complicated to use, so I don't use that. But people really like it, so that's good. But it's interesting because I've talked with Rosa Mekman, who's really big. She's an artist in the Netherlands, and she wrote like glitch. She's written like glitch manifestos. Somehow I think she got her PhD in like glitch, if that's possible, which is your doctor's glitch. But she's amazing, and we've talked at length about when what she thinks is like, what is it, glitch in the wild, or what is domestic, you know? And for me, it's not really that big of a deal. You know, I think it's, again, like I said, if people are looking for that look, I'm happy to write software that can kind of deliver that. But the interesting thing about doing it on a 6502 is that you aren't, like you said, with the JPEG, you're not moving that slider all the way down and getting compression. You just, basically, all you have to think is, what do I do correctly, and how could I do it wrong without everything screwing up? And that's kind of what I start to do when I do glitch nests. I'm like, well, what if that, like, you know, that screen, again, the screen rendering with the raster beam going down? Like, well, what if I try to make changes while the raster beam's rendering? Everything's going to go to hell. Well, how much can I push that before it just starts resetting? And that's the kind of thing you do. So it's interesting, like, glitch nest does all the right things for drawing to the screen, it just does it at the wrong times. And that's just kind of,
Or the right time.
or the right times, yes, depending. But yeah, that's kind of my...
So I should be closing this out. Let's see if there's... Do we have any questions from the audience? Come on. Nothing? Okay, good. Good. So I'm going to say, so let me close this out by saying that I think what you're doing is very valuable. I think it's like it's in historical context, even for something like the academy, right? Because most of the time we're on the proverbial cutting edge, whatever that means. And I think that there's a lot lost in the fact that not everyone has this base knowledge, which is why I got to the whole educator's question, right? Because this is a huge deal in computer science departments. Like, where do you start people? What does it mean to come out of an undergraduate computer science department with a degree? Like, how far does that go down the rabbit hole in terms of understanding what it is you're actually doing? Right, so we start people off on Java these days, which breaks my heart.
Yeah.
Because that's like, I don't think that's enough, but that's my personal take. So thanks a lot for doing that, and thanks a lot for being here. It's all